In the case of Meltdown, the problem is not speculatively looking past a bounds check, but speculatively looking past a page protection check, whether a page should be readable or not. It isn't actually obvious why this causes a problem. After all, different processes in an operating system have different mappings of virtual memory, completely different page tables. So why should a failed page protection check in one process somehow access memory through another process's page table? The reason is that prior to 2019 or so, operating system kernels tended to map all physical memory to some virtual address in every process. And a process just couldn't get to the memory of a different process through the protection bit as opposed to the page table entry not being there at all. The reason the operating system did this is because it's expensive to reset the whole page table. Much more expensive to do that than just adjust the protection bits. That is, our model of page protection in operating systems usually looks like this. The operating system has multiple processes, 1, 2, and 3, and each process has its own page table, its own mapping from virtual addresses to physical addresses. The virtual address hex 2000 in one process might map to different physical memory than the virtual address 2000 in another process. Maps to different physical memory because these processes are not supposed to share virtual address spaces. How do these virtual addresses get mapped to physical addresses so that the memory can actually be read? Well, you can have a table like this somewhere, but if this table is itself in memory, then every memory address needs to go do a memory address to find out what physical address it should actually look at. So the CPU helps an operating system resolve virtual addresses to physical addresses through a TLB, a translation look-aside buffer. This is a kind of cache, again, for mapping virtual addresses to physical addresses. If we stop running in one process and start running in another process, that means any cached value from the first process does not apply for the second process. So this TLB needs to be flushed whenever we're moving from one process to another process. And that is, in fact, how things work. Except that it turns out that when this process is running, some interrupt may happen so that the operating system needs to do a little work on this other process's behalf. It could implement that little bit of work by stopping the first process, switching over to the second process, which involves a TLB flush, and then going back to the first process, which would involve a TLB flush again. Instead of doing all of that flushing work, the operating system, while it's in process 1, also maps a bunch of its own virtual addresses into physical pages. It keeps these in non-readable mode most of the time, except when it goes into a mode that it's doing a little work on process 2's behalf while it stays in process 1. So instead of flushing the cache, it just uses these other addresses that are mapped to physical pages from other processes. So avoiding the TLB flush is the point there. But now we have within process 1 physical memory associated with other processes where the access is supposed to be guarded by page protection, but where a speculative read can get past that page protection. The solution to this problem is just don't do this. So operating systems no longer map all physical memory into some OS private range of the addresses. But to make that work out and to keep the program running fast, then the processor needs to help out and make it possible for the operating system to reach that other physical memory without having to flush the TLB. It turns out that this support was already in some processors before Meltdown was discovered, and so it was relatively easy to switch operating systems over to using that support.